Well, greetings, everybody. We are to the point where the first test examination is in. I want to share my screen here. And whoops, nope, I don't want to do that. I hit the end meeting for some reason. Okay. I want to hit the share screen, and we're going to share this screen, and everything is copacetic. Okay, what we wanted to do today is first talk about any of the homework, which is due for next time. Any questions at all on the homework? Again, I think that this is mostly for your edification, and I hope that you're mildly surprised at the results. At least that's what I hope. So anybody anybody have any questions? Okay, this is due the next time we meet, of course. Hearing no questions, this is really good news. I wanted to return to the ensemble average here. And I wanted to point out that ensembles can also be used for generating histograms. In fact, anything that you can empirically do for a random variable, you can do with this ensemble average. For example, you can compute the histogram at a point in the stochastic process if you generate an ensemble and then take that same point all the way down and sample all of these values and place them in a histogram. Okay, and that histogram is going to approach the probability density function in the way that we've talked about later. Could you also generate an empirical equivalent of a two-dimensional joint probability density function? And the answer is yes. You could generate a two-dimensional probability density function by doing the following. If this might be the value of t, and so you're generating the value at t, but then you could come down here. Boy, that wasn't a very straight line. Let's see if I need a straight edge to do this. Maybe so. Okay. Maybe we could come here and we could do, no, right here. And we could do a line which comes down this way. I can't even use a straight edge very well. So this is t and this is tau. And what one can do is, if we talked about before, we could make a histogram of tau versus t, and we could place these 2 points in this bin. I don't know what bin that is. We could place these 2 points in another bin, and we could build up a two-dimensional histogram like we talked about before. You remember the trucks, and we were measuring the length of the trucks and the weight of the trucks, and we generated a histogram. And that's exactly what we can do here also. So all of these things we can generate using an ensemble, if we have an ensemble of the stochastic process. So this is all well and good, and is just pointing out a generalization. You can do everything with ensemble that you can do with two-dimensional statistics. Okay, let's move on then. We've talked about random processes here. Last time we talked about the Gaussian. The Gaussian is pretty awesome. And with this, we defined a Gaussian stochastic process, right? The Gaussian stochastic process is that if you choose, you have a random variable here, and if you choose, not a random variable, but a stochastic process, and you choose any points, for example, these 2 points on the stochastic process, that this process, these 2 points, constitute a 4-dimensional Gaussian random variable. And if I were to choose 20 points, that would constitute a 20-dimensional random variable, et cetera, and et cetera. If this is true, no matter what your choice of points is, then your underlying process is indeed a Gaussian random variable. And then I think we proved the flip theorem. That was pretty straightforward. And now we're going to get into some more substantive stuff. So let's do that. We can talk about multiple random variables, and we have multiple random variables. For example, we have x of t and y of t. These are two stochastic processes, and we can typically, not always, but we can assume here that they are independent of each other. We're going to assume that if we have a stochastic process x of t, we have a stochastic process of x of t, and we have a stochastic process of y of t. If we choose any sequence of points, say for right here for t1, that line is supposed to be totally vertical. So we chose this point and this point. Okay, so that would be, for example, this is an x up here. It doesn't look like an x, does it? Okay, we'll make it more of an x. So that x of t1 is independent of y of t1, if you will. And literally, if we have these values here, and they don't even have to be the same, they can cross. So this can be the value of t2, and this can be the value of tau2. And what we're saying is that this point is independent of this point. So we can choose any sample here and any sample on y, or any sequence of samples on x and any sequence of samples on y, and those samples are going to be statistically independent. And this has to be true no matter what your values of k and j are, and no matter what your sample locations are. So it's a very strict sort of definition. Okay, here we have x of t and y of t. We could talk about the cross correlation between x of t and y of t. We know about the correlation, which has been defined. Many times we define the correlation as we have defined it previously as the autocorrelation. It's a correlation between the random variable and itself. But if we have a correlation between a random variable and another random variable, it's going to be something like this. By the way, many times you're going to have complex stochastic processes. We're not going to consider this here, but know that if we have a complex stochastic process, this second term is conjugated. So it's the expected value of x of t times y conjugate of tau. That's the definition if we have a stochastic process. And then the cross covariance, how do we get the covariance? Well, we take the correlation and we kind of subtract the means, and that's what we do for the cross covariance. We take the autocorrelation that we had here and we subtract the corresponding means at t and tau. And notice again, this depends on what t and tau is. We choose a x of t at some value of t. So it's going to be this random variable right here. And then we choose a y of t, or let's say a y of tau. I think that might be better to talk about. We choose a value of y of tau, and we have another stochastic process here. Here is the value of tau, and this is going to be y of tau. So when we talk about the cross correlation, we talk about the relation of this point at t and this point at tau. So the cross correlation in the most general sense, is going to depend on your values of t and tau. And man, that's a lot of t and taus, right? I mean, the different combinations that you have is just extraordinary. We're going to talk about some assumptions later on, which simplifies this and doesn't make it so incredibly strange. In the literature, you will hear of orthogonal random variables being written as the case where the cross correlation, the cross correlation is equal to 0. You're familiar with the idea of orthogonal. That's when the inner product of a couple of vectors is equal to 0. Then the two vectors are orthogonal to each other. We have a similar sort of situation here, except that idea of orthogonality is extended to a stochastic process. And it's orthogonal if the cross correlation of t and tau is equal to 0, then the two random variables are said to be orthogonal to each other. And they are uncorrelated. They are uncorrelated if the autocovariance is equal to 0. So these are some definitions. Let's talk about some multiple random variables. Here's an example. Here's an example. If we looked at the cross correlation here, I'm sorry, my microphone setup is getting in the way of my doing stuff. What is the cross correlation here? R sub x of t and tau, or xy, so it's a cross correlation of t and tau is equal to the expected value of the cosine of omega t plus phi times the sine of omega t, or omega tau. Notice, because the second value has to be tau plus phi. So this first term is what? That is x of t. What's the second term? The second term is x of tau. Notice that the random variable remains exactly the same in both cases. I always thought the capital phi kind of looked like a fat man, doesn't it? If you took this and put a couple eyes here, it looked like a guy that was really fat. So the capital phi, I guess phi for fat, the capital phi remains the same in both cases. So this in general is going to be the integral over theta of cosine omega t plus theta sine of omega t plus theta, omega tau plus theta, times the density function of theta, d theta. So again, this is kind of weird, since you're integrating over not the values of t, but you're integrating over the corresponding variable associated with the density function of phi. And so we could figure this out. For example, if phi, let's take theta, I'm sorry. Let's take an example of f sub theta. Suppose that theta went from minus pi to pi. If it went from minus pi to pi, that means it would be equally probable for a 360-degree rotation. In order to give the density function an area of 1, we have to have an amplitude of 1 over 2 pi here. So this would be the integral. Well, first of all, we have to put the 1 over 2 pi out front, so let's do that. Times the integral from theta is equal to minus pi to pi of the cosine of omega t plus theta times the sine of omega tau plus theta d theta. So under the assumption of uniformity, of the random variable theta, this is the result that we would get. And this is something you can work out, but you'll notice that there's some parameters here which don't change. Omega t and omega tau are considered kind of constants when you're doing the integration. So the result that you're going to get out is going to be a function of, it's going to be a function of t, right? It's going to be a function of t, and it's going to be a function of tau. And it's also going to be a function of omega. That's just kind of a tag-along variable. So it'll be a function of omega also. So this is how we can generate the cross correlation in a very easy problem of two sinusoids. Now, we said that they are orthogonal if r f sub x of t of tau is equal to 0. Do you remember that in the previous? If R sub x, x, y, if the cross correlation is 0, they're said to be orthogonal to each other. So if we go here and we look at this, the question for you is, do you think that this is equal to 0? In other words, do you think these stochastic processes are uncorrelated? One observation which should give you pause is that both of these random variables share the same random variable. I'm sorry, both of these stochastic processes share the same random variable, don't they? They share the same random variable. So yeah, I would think that, man, that'd be kind of weird if there was no correlation between the two and they shared the same random variable. But it might come up to that. I don't know. Let's look at it for the case. Let's look at it for the case of omega is, well, no, we don't even have to do that. Over this interval, we can perform this operation probably using something like Wolfram integration. I don't have the results of this integration over, on the top of my head, but it is something that we should be able to do, right, for the cross correlation. One of the places where we see cross correlation quite a bit in the area of electrical engineering is the signal and noise. We typically have a signal and then we have a corresponding noise. So we have a signal, x of t, which is kind of smooth right here, x of t. And then many times we have a noise which is associated with it. Now here's something which is interesting. Signals can be modeled as stochastic. Signals can be modeled as stochastic. I maintain, for example, if you are to record my words, and then you are to, if you were to record my words, that the audio that you would generate, the function of my vocalizations as a function of time in the future is a stochastic process. Because if it wasn't a stochastic process, it means it's deterministic. And if it's deterministic, that means that you can say, you can predict what I'm going to say in the future. It's deterministic, right? But what I say in the future is not determined at all, is it? It is indeed a probability. So my lectures, I hate to tell you guys, but my lectures and everybody else's lectures are going to be stochastic. They're stochastic processes. And so signals can be modeled as stochastic processes. So we have stochastic processes, and then we have additive noise. And this is the characteristic which is usually used, or this is the equation which is typically used in the characterization of noisy processes. Typically, a good model and a very commonly used model for a noisy signal is that it's the summation of a signal and noise. And we would like to assume that the noise and the signal are independent. So hopefully, if you have a noise source which is independent, independent of the signal, then the two values are indeed independent. So we can talk about the autocorrelation between the signal and the noise. But also, we've seen that if we add two stochastic processes, remember if we add y, forget stochastic processes. This is just back in statistics, right? If x and y are independent, the variance of x or the variance of y is equal to the variance of x times the variance of y. You remember we showed that when we considered things such as, do you see my microphone keeps falling down? I need something to prop it up. Let's try this. I'm going to use a box of tissues here to prop up my microphone. And hopefully it won't fall down now. So that being the case, since if they're independent, their variances add, the same thing happens with the variance of the stochastic process of y. The variance of the stochastic process of y is equal to the variance of x plus the variance of the noise. And we often talk about the signal to noise ratio. And remember the variance, if x is measured in volts, the variance of x is measured in what? Square volts, right? And therefore we'd like to take the square root of it to get back into volts. So to put things back into perspective, we often talk about the signal to noise ratio as the square root of the variance of x divided by the variance of the noise. So that's a typical definition of the SNR of two stochastic signals. And you can see here when we have a signal and a noise, this is a good place to talk about two unrelated stochastic processes, which we have been doing. Two unrelated stochastic processes. Now we are going to go through, I'm not going, well, I should say I'm not going to go through the discrete equivalent, but there are discrete equivalent stochastic processes, right? Where you have discrete time results. In fact, every time you cancel you store a stochastic process, some measurement on a computer, you need to sample it. Everything is stored in terms of vectors. We don't have continuous time on the computer. So anytime you are storing something, you are literally storing a signal digitally. You are storing a discrete time stochastic process. So just like the continuous value, and it's a straightforward generalization. It has a mean, it has a variance, it has an autocorrelation, and it has an autocovariance. A discrete time IID random process are so-called Bernoulli random variables and binomial random variables, and we're going to talk about those very quickly. Another one is called the random walk, and we will talk about that. It's also called the Drunkards Walk. We'll talk about the Drunkards Walk also in a minute. Well, let me tell you about the Drunkards Walk. Here's the idea. You got a guy, and this is a drunk guy, okay? So he's a little wobbly. And here is the origin. You can think of the origin as kind of a lamppost, right? And this guy is standing with the lamppost. And the first step that he does is he goes a distance in this direction, say a parameter, a distance of del. And he does it with a 50-50 chance. He can move to the right or the left with a 50-50 chance. And then he can move twice to the right with a 50-50 chance. And then he can move back to the left. So this will be the first step, the second step, the third step. And in each one of these, he is moving back and forth, depending how drunk he is, right? He's moving back and forth. Now, what is his position? What is his position? Or I should say, what is the value of x after n parameters? It's equal to the summation of, say, k is equal to 1 to n of a, let's see, I've used x already. Let me use a z sub n, where a z sub n is a bipolar stochastic process that says 50% I go to the right, 50% I go to the left. So each one of these is a Bernoulli trial. And that Bernoulli trial is either a +1 or a -1. Now, here is the interesting fact. What do you know about the distribution of x here? There should be a k. What do you know about the distribution of x if n increases? Z sub k's now, these are Bernoulli trials, either a +1 or a -1. What do you know about x sub n? What is that going to become? What kind of random variable?
Be it a Gaussian?
It's going to be a Gaussian because of the central limit theorem, right? So even though we start out with these random steps from the left to the right, we are going to end up x sub n eventually with a Gaussian process, which is kind of cool. So let's look at this sort of case. This is a generalization of the Drunkards Walk, where S sub n is equal to the summation of k is equal to n of x sub k. So this is a stochastic process. So we might talk about the Drunkards Walk, right? And we might talk about the position of the drunkard at each step. And so we can title this S, and we can title this S sub n. Now, in the first step, let's suppose that the drunk doesn't walk del, but it just walks a plus or a minus one, whatever units we're doing. So the first step, it might step to a one. The second step, he might step to a two. The third step, he might step back again. The fourth step, he might step to the other side of the lamp pole. The next step, he would step down here. The next step, he would step down here. Then maybe he would step back up here. And you get the idea, we're summing all of these random variables. We are summing the Drunkard's Walk in order to get his total position. S sub n is his position. So after 8 steps, he's going to have a position, it looks like here, of, I think, minus 2. Now, if we did it again, we might get a different value. We might get something like this. And every value, we have to move either a plus or a minus 1, right? So if we did the Drunkard's Walk again, we might get a stochastic process that looks like this. So if we repeat it again and again and again, we're going to get a different result. Now, this is the Drunkard's Walk that I've shown you right here. This is the Drunkard's Walk, right? Or the random walk, if you will. Random is probably more politically correct. I don't know. But the point is that it is a summation of a bunch of IID random variables. See, the x sub k's are assumed to be IID. So we're assuming that the second step of the drunk is totally independent of its first step, so that there's no memory in the process. Now, what can we say about this? We can say that, first of all, that the sum, if we take the expected value of both sides, we get the expected value of the sum, which we can write as S sub n with an overbar if we like. That is equal to n times x bar. Do we all agree with that? We've seen that before. And we've also seen that if we add up independent random variables, and they are independent, they're IID, independently and identically distributed, that we just add the variances. So the variance of S sub n is equal to n times the variance of x for this summation process. Now, we've talked about the Drunkard Walk. This is for any summation of samples from a stochastic process. Okay, what's happening here? Okay, my PowerPoint isn't moving for some reason. This happened last time. So let me try Control-Alt-Delete here, because sometimes that shakes it up. Huh. What the heck is going on? Okay, something happened. Okay, let me try something here. I'll stop sharing my screen and then I'll try to share it again. Let's see if that works. Okay, there it goes. Okay. So we forgot what we're going to do. We're going to try to find the autocovariance of this stochastic process. So that's what we want to do right here. We want to find the autocovariance of this stochastic process. So in order to do that, we go right to the mathematics. This is the autocovariance. It's the expected value of S sub n minus its expected value times S sub k times its expected value. Now, what is this? Well, let's see. This is the S sub n, and the S sub n is the counting process. And so we have something that goes like this. I don't know, something like this. And let me use S sub m here, where S sub m is equal to the summation of L is equal to 1 to m of the X sub L's, if that's okay. Now, what we're going to do is we're going to look at this process, first of all, for m is equal to n. Then we're going to look at this process for m is equal to k. And so we're going to have this random variable versus this random variable. Okay? And so we're going to have to do the cross correlation between this S sub k and this value here, which is S sub n. So we're doing the autocovariance between 2 points in the stochastic process. Now, in order to do this, if we go to the definition of the autocovariance, we get that it's equal to this times this. That's a definition of the autocovariance. And of course, S sub n here is equal to n times x bar. S sub k is equal to k times x bar. And we can manipulate this into simply the following relationship, into these two summations, because let's see what this is. The summation from n is equal to 1 to n is what? That's equal to S sub n. And what is the summation of I is equal to 1 to n of x bar? Well, that's nx bar, isn't it? So this is just a restatement of this result. Now, this is very interesting because of what happens here. First of all, if I is equal to j, we have a covariance. So let me do this. Let me do an n by k matrix here. And for the I, this goes from I is equal to 1 all the way up to n. And this one goes from j is equal to 1 all the way up to k. So think of this as a matrix. Wish I hadn't drawn those, but that's okay. So this is I is equal to 1 to n. This is j is equal to 1 to k. Now look at this. When I is equal to j, we're looking at each one of these terms, then we just have the variance. So we have the variance of x. Let's call this sigma squared, if you will. So when I is equal to j, let's say here, so it's equal to there because j is equal to 1, I is equal to 1. It's there, it's there. But pretty soon we're going to run out of room, right? Because n, at least in this case, is equal to j. So we have the variance across this diagonal of this non-square matrix. And otherwise, it's going to be 0. Otherwise, it's going to be 0. So it's going to be 0 here, and it's going to be 0 here. And we're going to sum up all of these things. Well, if we sum them up, how many of these do we have? We have n sigma squared, right? If we sum up all of the values within this covariance matrix, as we've seen before, we get n sigma squared. Now, this is under the assumption that n is greater than k, correct? We're assuming that n is greater than k because we've drawn this matrix longwise this way. If on the other hand, n is less than or equal to k, then it's equal to k times sigma squared. Because if n is less than k, we can kind of flip this matrix around and call this n and call this k, and the k's begin to win out. So we see that we don't have the wherewithal to fill up the entire matrix because of the top of this guy is going to be all zeros. And so we get indeed this result, and we can write this then as the autocorrelation. It's it's either equal to n times the variance of x or k times the variance of x, but it depends whether n or k is larger. So we can put this together and write this as the minimum of n and k. We choose whichever one is smaller, and we multiply that by the variance of x. I think I have this backwards, don't I? I'll see if you're following me and can do self-correction. If k is less than n, how many of these do we have? If k is less than n.
We would have k.
You have k, don't you? So I goofed it here. That should be k. And otherwise, it should be n. So I made a mistake there. Yeah, if k is less than n, we have just k of these sigma squared along the diagonal. And so that's the reason you get the minimum of n and k down here. Sorry for that mistake. So this is very interesting. So let's remember, let's not get caught in the weeds. Let's remember what this is about. This is about a counting process. This is S sub n is equal to a summation of IID random variables. I don't care what this random variable is. It can be Bernoulli, it can be Poisson, it can be anything that you want it to be. And what we've found out is the following. If we have one of these processes, which is called, it's kind of muffled on my screen. I don't want to do either one. I don't want to do that. How do I get her out of this?
I will try ESC. No.
No escape. There's no escape. I'll just put it down here.
If you click keep, does it ask you to save it to a file or something?
Yeah, it keeps it, and then it keeps all of the red stuff that I've drawn, and I don't want to do that.
Got it.
And it's giving me no choice. Okay, now my mouse is screwed up. Okay.
Well, and if you just hit the X, would it go away?
Use the what now?
Will it let you just click the X in the top right?
No.
And Alt F4.
Alt F4?
Yeah. No.
No, okay, I don't know what's going on. Okay, you let me go ahead and I guess I got to get rid of it. And, oh, I guess it just minimizes it. Okay. Okay, let me summarize again. Try not to screw things up this time. I wanted to point out that this is the autocovariance of a sum process. So we're talking about a sum process where we sum up these independent random variables. And we can also always say that the x sub k's are n x bar, the expected value of the sum, and the variance, because their IID, that's important to remember, their IID is equal to just n times the variance of a single result. And then what we just showed is that the autocovariance is equal to the minimum of n and k times the variance of x. It's the minimum of nk times the variance of x. And we did that by looking at the matrix, if you will. So that's true for any sum process. By the way, what's the asymptotic distribution of S sub n? Almost always it's Gaussian, isn't it? S sub n is eventually going to become Gaussian because of the central limit theorem. Unless, of course, you're adding up like Cauchy random variables, then it doesn't work. Okay, so let's look at a specific case. We've looked at the general case. Let's look at a Bernoulli sum process. For Bernoulli process, it's the variance of a Bernoulli trial. Do you remember the variance of a Bernoulli trial? The mean of a Bernoulli trial is equal to n, and the variance of a Bernoulli trial, I'm sorry, no, it's equal to p, isn't it? It's equal to p. The variance of a Bernoulli trial is equal to p times 1 minus p, and often we call this 1 minus p a q. That's common notation. So for a Bernoulli sum process, C sub S is equal to nk. Now, this is a Bernoulli sum process, assuming that all of the probability mass is either at 0 or 1. And this is referred to as a binary Bernoulli trial. It's binary because just like with bits, your outcome can be a 0 or a 1. We can also have a so-called bipolar case. Now, for the bipolar case, you don't have 0, you have -1 and 1. And that turns out to be the bipolar case. Now, we're going to use the bipolar case in the Drunkards Walk, right? Because the Drunkards Walk can either go -1 or it can go +1. So that's for the bipolar case. And so it turns out the variance for the bipolar case is equal to 4QP. And that means that the autocovariance for the bipolar case, if we do a sum process, is equal to 4 times the minimum of nk times pq. Notice this mk, this minimum operation is applicable no matter what the sum of the processes are. And does that kind of make sense? Because look, if you think of a sum process, we're going out here to k, and then we're going out here to n. And it's kind of like the variance, both n and k share the same stochastic process, right? Up to k. And then after k, that stochastic process is totally on its own. So there's no interrelationship things happening here. So we should expect that only for the minimum value, in this case, k is the minimum, only the value of their shared space is going to give us a contribution to the overall autocovariance. Okay, let's look at Poisson random points. This is also kind of interesting. We're going to place n points randomly on a line of length t. So we're going to derive a totally new stochastic process here, the Poisson stochastic process. So here we have a interval of length t, and then we're going to choose a small value of t here, and we're going to place points uniformly along the point of t so that some of them are in the smaller interval, some of them are not within the greater interval. So here's the points. I'm placing them. Do you see me placing them? Okay. Lots of animation went into this, so I hope you enjoy the animation. Okay, here we're going to choose a subinterval of length t. So here is the subinterval of length t. Now we ask ourselves, what is the probability that a point lies within this smaller interval? Well, you notice this is nothing more than a repeated Bernoulli trial. It's a repeated Bernoulli trial. And what is the probability? The probability of getting a point within this smaller interval is just, well, it's t over t, right? It's the smaller interval divided by the larger interval. In fact, we have it written down here. And this turns out to be a repeated Bernoulli process, doesn't it? Because each result is either a success or a failure. So it's a repeated Bernoulli process. So we get then that the probability of choosing k points in the interval t is given by the binomial distribution, or the binomial term, which is shown here. That's something that is relatively well known. Okay, so that's all well and good. So we're going to do something now. We're going to make k big. What is k? That's the total number of successes we have, and the probability of success small. And here's what we get. We get the probability of k points in this is approximately equal to this, which is a Poisson. So this is interesting. A binomial, in certain cases, can be approximated by a Poisson. How many have seen this approximation before? Okay, nobody has. Okay, we'll kind of give you a engineer's proof of this, but here's the point. P is equal to little t over big T. So I'm going to take P here and substitute little t over big T in the following expression. And that's what the probability of k points is if we make the k big and the p small in the right way. Okay, let's take a look at this. This is the claim that we make. It's referred to as the Poisson approximation. And here's why. Let's take, first of all, a look at this point. N choose k. Okay, n choose k is equal to this in terms of factorials, right? Now, if k is small, if k is, k is very, very small with respect to n, then this is about equal to n to the k. Why is that? Because suppose that we have something like n is equal to 1 billion. So we have 1 billion times 1 minus 1 billion times, we have 1 billion times 1 billion minus 1 times 1 billion minus 2 times 1 billion minus 3. Isn't that about the same as 1 billion to the 4th power, right? Do you see that? So therefore, if k is a very, very small number, then we can make this approximation. Also, we can make the approximation that first of all, we can bring this n to the k forward, or this k factorial forward. And then we can do, and then this is the result that we get. That's about equal to n to the k over k factorial. So it turns out this is about equal to n to the k over k factorial. N to the k over k factorial. So we now have to still get in this p to the k and e to the minus nk. Where does that come in? Well, that comes here as follows. Q to the n minus 1, which is this term. Q to the n minus 1 is 1 minus p raised to the n minus k power, because q is nothing more than 1 minus p. And again, if k is small with respect to n, this is about equal to 1 minus p to the n. We can forget that k. But this is the approximation for e to the minus p. These are the first two terms. We use this, by the way, in the proof of the central limit theorem. We use this approximation. So this 1 minus p to the n is about the same as e to the minus p raised to the n. This is under the assumption that p is a very, very small number. The p is a very, very small number. And so we have e to the minus pn, and that takes care of e to the minus pn. Well, this is e to the minus np, and we have this result taken over. So therefore, we have kind of, if you will, proven the Poisson approximation. So let's take a look back now that we've kind of given a thumbnail sketch of the proof of the Poisson approximation, and look at the probability of k points on this interval. Don't forget, we have a value of t here, and we have a subinterval of small t. And the p is equal to the ratio of little t to big T. Now what we're going to do is we're going to let n go to infinity. In other words, we're going to place an infinite number of things on here. But we're going to let n go to infinity, but we're also going to let t increase so that the ratio of the number of points to t stays the same. And we're going to call this lambda. So again, we're going to do a point like this, t. Here's little t. Now we're going to, and we put 10 points here. So we have 10 over 10. So we have the same exact points. Now we're going to double the value of t, or maybe make it really bigger, say t is equal to 100. We're going to keep little t the same. But now instead of 10 points on here, we're going to put 100 points on here. Here, over here, we put n is equal to 10 points in here, so that the ratio of the number of points to t is 1. Here, the ratio of the number of points is still 1 to 1. And we're just going to let this value of t get bigger and bigger and bigger while keeping this interval of little t exactly the same. So we might go to n is equal to 10 to the 10th, and then this big T turns out to be 10 to the 10th wide, okay? So we do that, and we keep this lambda is equal to n over t frequency points, a constant. We're going to call this lambda. So this being the case, notice that we have an n over t here, and we have an n over t here, right? So both of those we're going to call lambda. We're going to call n over t lambda. And doing so then gives us the k points on the interval t, e to the minus lambda t times lambda t to the k over k factorial. This turns out to be a very important model of stochastic processors, or for uses in stochastic processes. What it tells us is what happens for Poisson processes. And these Poisson processes are everywhere. And we'll talk about a few of the places that they're available at. But my favorite is when popcorn pops. Popcorn pops at a, if you listen to popcorn pop, it goes pop, 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 right? That turns out to be a Poisson process, at least in the middle of it. You know, in the beginning, it's slower. In the end, it kind of dies down. But in the middle of popcorn popping, each one of the pops and the occurrences is a Poisson point. And we can model this as equal by a parameter lambda. What is lambda? That's the average number of pops per second that we have. We can also model this if we go out onto University Avenue, and during a certain time of the day, we count the cars going by. Car, 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 car. Notice that's a lot like popcorn popping, isn't it? And we could talk about lambda there. That lambda for the cars is the average number of cars that is going by per second. The lambda for popcorn is going to be a lot bigger than the lambda for cars, isn't it? Right? Because the lambda for popcorn is really quick. Pop, 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 pop. Whereas the cars will go car, 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 car. The lambda would be a lot smaller. So we see these Poisson processes as very ubiquitous in the world, and this result is very useful. It's also used quite a bit as a model for queuing theory. If you look at people arriving at, say, the checkout counter at Walmart, and let's suppose that you have one checkout counter at Walmart, And let's assume that people begin to arrive there. The people arriving there is many times modeled as a Poisson process. Arrival, 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 arrival. So that's another Poisson process. And anyway, the point is it's incredibly ubiquitous and is used extensively in a number of areas of engineering and other places. Here is the important point. The only thing that a Poisson process requires in order for definition is lambda. Lambda is the average number of occurrences per second. It's a parameter of the stochastic process. As we mentioned, lambda for popcorn is going to be a lot larger than the lambda for cars going by on University Avenue. And here's the point. If you have something with a process of lambda and you want to find out the probability of k occurrences on some interval k, some interval t, the probability of k points on t is equal to, and this is really cool, lambda t to the k over k factorial. And this comes from the previous slide. I'm sorry it's obfuscated here, but you can see that it's lambda t and this lambda t. And so if we have a time interval, we can find out the probability of generating k occurrences over that time period under the assumption that we have a constant sort of process. And there are a number of examples. I mentioned popcorn. Rain on the rain. If you hear rain, if you can imagine rain, it goes splat, 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 splat. That's a Poisson process, or could be modeled as a Poisson process. Passing cars we've mentioned. We'll talk about something called shot noise, which is something that happens in electronics, and packet arrival times. If you look at packet arrival times, say at a computer, over a certain period, it is typically modeled as a Poisson process. Now, the Poisson process that we have done assumes that there is a constant lambda, that lambda is the same all the time. You know that if you pop popcorn, the lambda, first of all, the number of pops per second as you start out is going to be much smaller because it'll go pop, pop, pop. You go pop, 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 pop. So the lambda actually changes. So there's models of the Poisson process where you can use the value of lambda changing. But for our purposes, we're going to assume that lambda is a constant. So here we have Poisson points. Now these Poisson points do not define a stochastic process. They're only points on a line. A stochastic process has to be a time series, either discrete or continuous, that uses a random variable, that contains some sort of random variable. Here we don't have any, here we don't have anything stochastic other than the points. We don't have a function, if you will. Stochastic process has to be a function, stochastic function. So one of the things we can do is do a Poisson counting process. And every time there's an occurrence, we go, guess what? There's a Poisson point, the first Poisson point over here, I'm going to shoot up to 1. Okay, I'm going to go over and I'm going to wait for the second Poisson point to come here. And then this new Poisson point and a new Poisson point. And we can count this process. Some of you have heard of photon counters that count the arrival of photons. And by the way, if you have a very low light source, then the arrival of photons on a photodetector can be modeled successfully as Poisson. And so if we have a counter, a photon counter that counts the number of photons coming in, this is what the counter will look like. It's counting the number of photons that arrive. All of a sudden now we have a stochastic process. We have a process that we can talk about in terms of means and variances and autocorrelations and all of that other stuff. So recall that for a Poisson random variable with a value of A, that the expected value of a Poisson random variable with A had X bar, and this was curious. We talked about this. X bar was the same as the variance of X. Remember, we talked about the curious question of, whether X bar and the variance of X should have the same units. It looks like the variance of X should have the square of the units. So if X is volts, then X bar should be volts and variance of X should be volts squared. But it doesn't quite apply here. And the reason is we're doing counting, and counting is a unitless process. So we don't have any counting. So this is the result that we get from the Poisson process. We get that if we have this as the probability density function for a Poisson random variable, that the mean and the variance are both equal to X. And so, the mean and the variance are both equal to the parameter A of the Poisson process. We can apply the same thing to the Poisson counting process. And we can say that the expected value of X of t is equal to lambda t. And this is also equal to the variance of X of t. They're both the same thing. Now, at this point, I go into a protracted derivation of the autocorrelation of the Poisson process. I've decided to skip this because I think we would get so deep in the weeds in terms of the mathematics that it would be it'd be kind of terrible. So let me just kind of skip forward. And point out, this is interesting, the autocovariance of a Poisson process is equal to lambda times the minimum of t and tau. Do you remember when we had counting processes that we had this minimum here depending on which was larger, t and tau? So we have the same thing with a Poisson counting process. So we have this Poisson process, and this is a function of t, and so we have a value of t here, and we have a value of tau here. And so therefore, if we look at the autocovariance, we get that the mean is equal to lambda. It's either equal to lambda t, which is this value, or lambda tau. But since in this case tau is greater than t, only this first part is shared in the counting process. So it's equal to lambda times the minimum of t and tau. There are different processes also related to the Poisson process. One is the random telegraph signal, wherein you have a number of Poisson points, as you can see here. And every time you miss, you hit a Poisson point, you can think of a light switch. You switch the light switch to the different result. So the light switch starts on, you hit your first point and it goes down and it turns off. Then you hit your next point and it goes up and it turns on. And then you hit your next point and it turns off. So what you get is kind of a stochastic stair wave, if you will. And that is another signal, another stochastic signal other than the counting process, which you can generate from the Poisson random variable. And I will show you here that the expected value of X of t is equal to this, and the autocovariance is equal to this. This is going to turn out to be very important later on as we talk about some different things. But here's the thing. This is why the expected value is not equal to a constant. If we look at this telegraph signal, what does it always start out as? Always starts out as 1, correct? It always starts out at 1. That was our convention. And then it goes down and it does this, and then, it does something like this. Now, here's the point. When we're here, we know that the expected value is equal to 1 because all of the stochastic processes, all of these telegraph signals start at 1, don't they? They all start at 1. As you get out here, larger and larger, I don't know, the number of times it's gone up and down is so weird that you really can't keep track of it. And you get a mean of 0. Since way out here, gosh, it changed so much, it could either be a +1 or a -1. We're not sure. So the average of 1 and -1 is 0. So we would expect this to go to 0 some way. So for this reason, we have, a mean here equal to x of t, which is equal to 2e to the minus alpha t. So the mean is equal to 1 at the origin. It's always equal to 1. In fact, the variance of the stochastic process at the origin is always 1. But then the mean gets smaller and smaller and goes asymptotically to 0. We're going to be using later the flip theorem. Do you remember the flip theorem? Is we flip a coin, and with a 50-50% chance, we flip x of t to y of t. Times x. So it has a 50-50 chance of staying where it's at, or it has a 50-50 chance of just negating itself, right? So it has a 50-50% chance of staying this solid red, and it has a 50% chance of flipping over and becoming the minus value. Now, in that case, what is the expected value of the stochastic process? Can anybody hazard a guess?
Be 0.
Yeah, it's 0. We showed with the flip theorem that the autocorrelation, that the expected value is always 0 because of the flip theorem. I don't care what stochastic process you have, right? And what about the autocovariance? Well, let's do the autocovariance of y. We also showed in the flip theorem that the autocovariance stayed exactly the same, didn't it? This was a result of the flip theorem. So the expected value and then the autocovariance stays the same. The expected value in the flip theorem is always 0, and the autocovariance always stays the same. This is something we proved, I think it was last lecture. Okay, next I'm going to skip this because this is really a weird derivation and it gets down to the weeds, and you will thank me that I skipped all of this math, okay? And this is the proof of those assumptions about the mean and the autocovariance of the Poisson random signal or telegraph signal. Aren't you glad we're skipping this? I tell you, it's beautiful math. I really like good math. Heck, I like bad math. Okay. The last thing that we'll do, and I think we'll take it up this time, next time, but we will look at a Poisson process, which we call Z of t, and this Z of t will have a Dirac delta every place where you have a Poisson point. This turns out to be very important. So every point here, we have a Dirac delta. Why is this important? Because we can use it to model things such as shot noise. Shot noise happens when an electron hits or a photon hits a photodetector. What you get is the photon hits and it goes wiggle, wiggle, wiggle. And another photon hits and it goes wiggle, 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 wiggle. And another photon hits and it goes wiggle, 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 wiggle. It does kind of the same wiggle, wiggle all the time. And so this is H sub t, H, if you will. Each one of these is an H. And each one of these H's starts at a Poisson point. Okay? And the reason that this is kind of cool is that you can take and you remember this from linear systems theory. If you take an LTI system with an impulse response of H of t, then the output is going to be what? Z convolved with H, correct? And what happens if you take something, if this H of t is a wiggle, wiggle, wiggle? What are you going to get out? You're going to get out every place there's a Poisson point. If you convolve this with this, every place there's a Poisson point, you're going to get a wiggle, wiggle, wiggle. So therefore, this Z of t, these Poisson Dirac deltas, proved to be a useful signal in the characterization of shot noise, because one detector might have one value of H of t, another detector might have another value of H of t, but you can use whatever value of H of t it is for that detector, photon, electron, whatever, and you can then convolve it with the Z of t, these Dirac deltas at the Poisson points, because these arrivals of the photons, for example, occur in accordance to a Poisson process, and we get a very nice representation of the underlying signal that we measure. Isn't that cool? So Poisson points are everywhere, and Poisson stochastic processes are everywhere. Okay, there I have another example of an H of t with the solid blue lines. And then I tried to add them, those two overlapping blue lines I would have to add. Okay, and then next time we get together, we'll talk about the Wiener process. This is named after Norbert Wiener, who has the coolest name in the world, Norbert Wiener. And we'll talk about him next time. He's the father of cybernetics. Norbert Wiener actually derived the term cybernetics. He invented it. And we'll talk about a Wiener process next time, which is very important for things such as the movement of the stock market and the way that, and the way in Brownian motion, which little molecules of water bump into small pieces of paper. And that was what Einstein wrote about in 1904. It was one of his year of miracle papers where he wrote these 4 incredible papers. And we'll talk about Wiener processes next time. Any questions at all? Okay. Okay, that being the case, then goodbye and be of good cheer.